In Module 11, Section 3, we will learn how to simplify radical expressions. First, let's look at the product rule for radicals. If we have two radical expressions with the same index and we're multiplying them together, we can write one radical sign with the same index and multiply underneath the radical symbols. Let's try to use the product rule to multiply these next few examples. We start with the square root of 3 times the square root of 5. It's important that they are both square roots, otherwise this product rule wouldn't work. But because they are both square roots, we write the square root one time, we have the square root of 3 times 5, which becomes the square root of 15. Let's try another example. We have the cube root of 4 times the cube root of 2. That becomes the cube root of 4 times 2, or the cube root of 8. Now this example is different than the last example because 8 actually has a cube root. The cube root of 8 is 2. We know that because 2 raised to the third power is 8. We can also use the product rule when we have fractions underneath the square roots. We have the square root of 2a times the square root of b over 3. We multiply. We have the square root of 2 over a times b over 3. Multiply your numerators together, 2b. Denominators, a times 3 is 3a. That is all underneath the square root. We also have the quotient rule for radicals, which states if we have a fraction underneath one radical symbol, we could rewrite that as the root of the numerator and the root of the denominator. The same is true if we start with the right-hand side. If we have two of the same radical, same index, we can rewrite that as one fraction. Let's try a few examples. Here we have the square root of 5 over 16. We can rewrite that as the square root of 5 over the square root of 16. We note the square root of 16 is 4. The square root of 5 doesn't reduce. So we have the square root of 5 over 4. In the bottom expression, we have the square root of 40 over 81. That becomes the square root of 40 over the square root of 81. 81 is a perfect square. The square root of 81 is 9. With 40, we need to make a prime factorization. We take 40, and 40 is 2 times 20, which is 2 times 10, which is 2 times 5. And because we're taking the square root, that tells us we need two identical factors to form a group. So we have two 2's. They form a group, so we bring a 2 outside of the square root. But we also have two factors that we're not able to form a group, 2 times 5. And 2 times 5 is 10. So our simplified expression is 2 squared root of 10 over 9. Let's try to simplify a radical. Here we have the square root of 300. Just like we've seen and done already in a few examples, we're going to make a factor tree. We start by dividing by prime numbers. So we divide by 2. It gives us 150. 2 is prime. 150 divided by 2 is 75. Again, 2 is prime. 75 we can divide by 3. And 3 will go into 75 25 times. 3 is prime. 25 is 5 times 5. And both of these 5s are prime. Because we're taking the square root, and let's just write the prime factorization up above, 300 equals 2 times 2 times 3 times 5 times 5. But because we're taking the square root, we want a pair of identical factors to form a group. So we have a pair of 2's, a pair of 5's, and the 3 left over. Any pairs, we will multiply those groups together. So I have a pair of 2's that represents 2, a pair of 5's that represents 5. 2 times 5 is 10. So we were able to pull 10 out from underneath the square root. However, there will be a 3 left underneath because it could not form a group. Let's now try to simplify the square root of 15. Well, if we make a factor tree for 15, that breaks down to 3 times 5. We can see here we don't have any pairs of identical factors, so we can't break down the square root of 15. We'll just write it as square root of 15. Let's now try to simplify some radical expressions with variables. In the first expression, we have the square root of x to the 7th. Remember, the index here is 2. We've already shown the trick in the shortcut of using long division with the exponent and the index. If we do that, 7 divided by 2, 2 goes into 7 evenly 3 times. 2 times 3 is 6. And so we have 1 left over. We have a remainder of 1. This means that we will bring 3 factors of x outside of the square root, or x cubed, and we will have 1 factor of x left underneath the square root, just x. Let's do the same thing with the next expression. Here we have the square root of 20 over x to the 16th. We can rewrite this as the square root of 20 over the square root of x to the 16th using the quotient rule. For the square root of 20, because 20 is not a perfect square, we make a factor tree and eventually the prime factorization for 20. The prime factorization for 20 is 2 times 2 times 5. Because we are taking a square root, we take identical factors. If we have a pair, out from underneath the square root. So we bring out the 2, but the 5 has to stay underneath because it doesn't have a pair. In the denominator, we take 16 and divide it by the index, which is 2. 16 divided by 2 is 8 with no remainder. So we bring out 8 factors of x, or x to the 8. Let's try another example. We want to simplify this radical, the cube root of 54 x to the 6th, y to the 8. We start with the number. Make a factor tree for 54. 54 is 2 times 27. 27 is 3 times 9. And 9 is 3 times 3. Because we are taking the cube root, we want 3 identical factors to form a group. Let's write the prime factorization of 54, 2 times 3 times 3 times 3. And here we have 3 identical factors, but the 2 is left over. So the 3 identical factors come out as one number, 3. But the 2 that doesn't have a group that it can form stays underneath the cube root. Now let's go to the x variable. We use long division on the exponent. We take the exponent divided by the index. So for the x's, take 6 divided by 3. 3 goes into 6 2 times with no remainder. So we bring 2 factors of x out from underneath, and none remain underneath the cube root. Let's do the same thing with our y's. We take the exponent 8 and divide it by 3. 3 goes into 8 2 times evenly with 2 left over. This means we bring 2 factors of y to the outside, 2 factors of y stay underneath the radical symbol. Let's use the quotient rule to divide, then simplify if possible. So now we're going to use the quotient rule in reverse. If I have the square root in the numerator and square root in the denominator, I can write one large square root with a fraction underneath. And sometimes that's nice because now we can simplify the fraction. 20 divided by 5 is 4. So that becomes the square root of 4, which is just 2. Let's do the same thing in this example. We have 7 cube roots of 48y to the 4th over the cube root of 2y. So we rewrite this as 7 times one huge cube root, 48y to the 4th, all over 2y. This becomes 7 times the cube root of, when we divide, 48 divided by 2 is 24. Y to the 4th divided by y, we subtract the exponents. That becomes y cubed. Now off to the side, let's write the prime factorization of 24. 24 is 2 times 12, which is 2 times 6, which is 2 times 3. So the prime factorization is 2 times 2 times 2 times 3. Because we are taking the cube root, we need 3 identical factors to form a group. We have 3 2's. So we form one group with a number left over. We bring the 2's to the outside as one number, so we have 7 times 2. We multiply the number that's already there. Underneath the cube root, we are left with the 3. We now look at the variables. We only have one variable. So we look at the y's. We take the exponent, which is 3, divide it by the index, which is 3. 3 goes into 3 one time with a remainder of 0. That means we bring out one factor, and we have no factors remaining underneath the square root. So if we continue to simplify, 7 times 2y is 14y times the cube root of 3. In this section, we are also going to look at the distance and midpoint formulas. By using the Pythagorean theorem, we can derive a formula for finding the distance between two coordinates, x1, y1, and x2, y2. And you see the equation listed below. So let's try to find the distance between 2 points, -5, 8, and -2, 2. First, let's label our points, x1, y1, x2, y2. Once we do this, we're going to plug into the distance formula, and I'll let you know now that you will need to memorize the distance formula. It will not be given to you like this on any test if you have any test questions. But we're going to plug in. This gives us d equals the square root of x2 minus x1 squared, so -2 minus -5 squared, plus y2 minus y1 squared, 2 minus 8. squared. This becomes -2 minus -5 is the same thing as -2 plus 5. So this is the square root of 3 squared plus 2 minus 8 is -6, so -6 squared. That gives us the square root of 9 plus 36. And 9 plus 36 is 45. So we have the square root of 45, but we're not finished because we need to try to simplify the square root. So we take the prime factorization of 45. 45 is 5 times 9, which is 3 times 3. Because it's a square root, we want two identical factors to form a group. We bring the 3's to the outside, and the 5 has to stay underneath because it could not form a group. This is the midpoint formula, and the midpoint of the line segment is the point directly in the middle. We're given the endpoints, and essentially we're averaging the x coordinates and averaging the y coordinates. So let's find the midpoint of the line segment that joins points P with coordinates -5, 8, and the second point, -2, 2. So let's label the first point x1, y1, and the second point x2, y2. And just like I mentioned on the previous slide, we're going to average the x values and average the y values. And so we add the x values, -5 plus -2, divide by 2. We average the y value, so we add 8 plus 2 and divide by 2. We now simplify. -5 plus -2 is -7. That's over 2. 8 plus 2 is 10, and 10 divided by 2 is 5. Make sure to write the midpoint as an ordered pair because the midpoint is an actual coordinate. The distance is just a number.